Next, we turn to describing some popular discrete spacetime models. These models all involve some notion of discreteness and some notion of causal structure, although some of them may even incorporate spatial structure and some other types of structure. The first is spin foam, which we see in loop quantum gravity. They are essentially evolving spin networks. If we begin with a spin network, then its structure can change as time goes by, and the result is a sort of cellular complex called spin foam. Of course, the spin network has additional information attached to it, but for our own purposes, we are only going to focus on basic combinatorial structure. Another model is causal dynamic triangulation, which we build up a spacetime by gluing together small four-dimensional simplices. A third model, which we already mentioned before, is causal sets. They are simpler than spin foams or causal dynamic triangulation, since they do not involve any additional structure rather than elements or relations. Fourth, we are going to work with somewhat more general class of structure that are similar to causal sets but involve slightly different features. We call them directed sets, although we do have to be careful with the terminology, as we will explain a little later. The example we have drawn right here has cycles that are closed causal curves, but we will mostly use acyclic directed sets. Causal sets are example of acyclic directed sets, but they have some requirements that we don't want to impose, like transitivity. Finally, there are a lot of other discrete models which we do not have time to describe. Now we are going to focus on directed sets, which are often called directed graph in other settings. Mathematically, a directed set is just a set equipped with binary relation, which tells us which of the elements are related to which other elements. We often use a single symbol D to denote such a directed set, but you should remember that there is binary relation in the background. The physical interpretation of directed set is exactly what you would expect. The elements represent space-time events, and the relation represents the direct influence between the pairs of space-time events. These are simple basic assumptions we could make if we want discrete space-time structure with cause and effect. Remember that the reason why we want these features is because the causal structure gives us conformal structure according to Hawking and Malamud, and the discreteness gives us the scale data. We include here the disclaimer that mathematicians use the term directed sets to mean something else, but we find it convenient to say sets here instead of graph. It's worthwhile to notice that the theory we developed by studying these directed sets is applicable to many different discrete models. In particular, we can begin with spin foam, causal dynamic triangulation, or causal sets and ignore some of the structure to get directed sets. In case of causal sets, we don't have to ignore anything because they are special cases of directed sets. But anyways, the behavior of these objects will depend to a large degree on the behavior of the underlying directed set. We show some pictures right here. We can take a spin foam and obtain a directed set just by following how the nodes in the spin network evolve. Or we can begin with the causal dynamic triangulation and associate one element to each simplex and one relation to each space-like phase. There are actually a number of different ways we can do this, but the point is that the large part of the structure is purely discrete causal. We can only obtain very general results by just working with this part of the structure. With causal set, as we just said, we don't have to ignore any structure. And of course, the whole point of this is to obtain a flexible theory that will apply to many other different discrete models. Now we have to get a little bit technical and talk about some building blocks of structure in directed sets. First of all, a chain is just a sequence of consecutive elements and relations. The length of the chain is just the number of relations involved, so a zero chain is a single element and one chain is a single relation, and so on. Chains represent the flow of influence or information in the directed set. In this picture, we are assuming that the information flows up the page, which is a convention that works in acyclic directed sets. We spell this out a bit later. An antichain is a kind of like an orthogonal complement of the chain. It is a set of elements that are completely unrelated in a sense that they don't have any chains connecting them. The physical interpretation that an antichain is like a spatial section of space-time. Such sections are very important for dynamic purposes. For example, a special type of spatial section in relativistic context is Cauchy surfaces. The magic of relation space theory that we mentioned before is that maximal antichain in a relation space are impermeable, which means that they can serve as a discrete analog for Cauchy surfaces. But we won't go into that detail right now. Next, we talk about cycles. A cycle is just a closed chain. A directed set is called acyclic if it has no cycle. Individual elements don't count as cycle. A cycle has to include at least one relation. The physical interpretation of a cycle is a closed causal curve or time travel scenario. We repeat one of our little pictures from previous slide representing an individual who is his own father and son. These sort of things happen if you allow cycles. There's nothing necessarily contradictory about cycles, but we choose to focus on acyclic cases for now. This lets us apply a graphical convention that we have already used several times, where we abstain from drawing arrows to indicate the direction of relation and assume that the direction is always up the base. We will follow this convention from now on unless stated otherwise. It isn't always convenient to talk about the entire universe, so we have to consider a localized reason of the discrete spacetime model. This leads us to the discussion of subobjects of directed sets. A subobject is just a set of elements of D' and a set of relations where the relations are between the elements of D' and not between other elements somewhere off in and some unrelated part of D. The physical interpretation of subobject, of course, is a local spacetime reason. There's a potential complication which is worth mentioning. When we talk about a subobject, do we include all the relations of D between its element or only few of them? If we include all of them, we call it full subobject. In most cases, we will deal with full subobjects. The picture shows the difference between the two. Essentially, if a subobject is not full, then it is missing some possible relations, whereas a full subobject inherits all the available relation structure from D. It's a nuisance to keep writing binary relations over and over again, so we will often denote a subobject by just a set of elements D'. When we do this, we are implicitly including all the possible relations unless stated otherwise. So we are treating D' as a full subobject. For the purposes of observation, past and future are the most important subobject of directed sets that we can consider. The past of a subobject D' is defined mathematically to be the set of all the elements X in D that are connected to elements of D' by ascending chain. This means that we can begin at X and then follow a sequence of relation upward until we hit an element of D'. This picture here on left shows a single element X in the past of D', and the picture on the right shows an entire structure of past of D'. Notice that the most of D' belongs to its own past because most of the elements of D' influence other elements of D'. The only exceptions are the maximal elements of D'. The physical interpretation of past of D', of course, is that it is everything that influences D'. We usually take into consideration all the relation between the pairs of elements in past, so we consider this as a full subobject of D'. We have a slide about future, but we could really just say it to flip everything around, and it would all be self-explanatory. The future of D' consists of all the elements of X connected to an element of D' by a descending chain. So if we look at the picture, we can see that this means that we can begin at any element of D' and follow a sequence of relation upward until we hit X. The rest of the slide is pretty similar to the last one. The physical interpretation of future is everything influenced by D', and we usually think of it as a full subobject. So far, we've been working classically, comparing individual directed sets to individual spacetime manifold in context of general relativity. But of course, our whole objective is to study gravity in quantum setting. There are many different approaches to quantum theory, but one of the features that all of them possess is some version of superposition, where we combine together different states of some sort. Gravity is a way of talking about structure of spacetime, so in quantum gravity, we have to combine different spacetime. In discrete causal theory, these spacetimes are modeled into discrete directed sets. So we have to consider an entire configuration space of these directed sets. Here we have an illustration of a very small part of such configuration space. Inside each large colored nodes are individual directed sets. The line connecting the large node represents evolutionary relationship in which one directed set grows into another one by adding new elements and relations. In this particular case, we are adding only one element at a time, so evolutionary process here is called sequential growth process. There's a famous paper by Rideout and Shorkin on sequential growth dynamics on causal sets. This is a similar picture except that we include some additional non-transitive directed sets that are more general than causal sets. Here the causal set appears inside the blue node and the non-transitive directed set appears inside the red node. The reason we included the non-transitive set is because it allows us to model indirect causes better and because overall configuration space behaves better that way. It seems that the most promising way to do quantum theory in this setting is by modifying Feynman's path summation approach, which is also suggested in Rideout and Shorkin's paper. In this case, the path that we sum over are actually evolutionary pathways on the configuration space. Later on, we will elaborate a little bit on the interesting fact that the configuration space itself has a higher level structure, which is very similar to the structure of its individual member. Overall, however, we won't need many details of quantum theory in order to introduce what we need to discuss about quantum observation.